Okay, our next topic is theorem of Schur, who proved the following in 1916. So for any R, there exists N such that in every R coloring of the integers n from 1 to n, so right, there exists x, y in n such that x, y, and x plus y have the same color. So no matter how you color the positive integers with finitely many colors, you have two integers x and y such that x and y and x plus y have the same color. And the proof is easy. As soon as you use Ramsey's theorem, you can prove it. So let chi be a, okay, I need to take n to be something. So let chi be an R coloring. Right? So what I do is we construct the complete graph on n plus 1 vertices. And color, so this graph is on the vertex set 1 up to n plus 1, and color on edge ij with chi of the I minus j, right? So if you have a like K5, right? This is 1, 2, 3, 4, 5. Then I color this edge by color of 1, this edge by color of 4, etc. Now what we do, so now this is an R coloring of the edges of the complete graph. So if my number n is equal to Ramsey number of what? R minus 1. Okay, so this number of times is, oh no, not R, let's say 3. Right. Now, by the Ramsey's theorem, there exists a monochromatic triangle. Right? Let's say there exists A, B, C, right? Okay, distinct A, B, C in M such that chi of A big B and chi of B big C is equal to chi of A big C, right? So that's the triangle where all the edges have the same color. Why? Because n plus 1 is equal to the Ramsey number. Now this implies, so let's assume A is less than B is less than C, and then chi of B minus A is equal to chi of C minus B is equal to chi of C minus A. But C minus A is equal to C minus B plus B minus A. Right? So let's take this to be, so take x to be equal to C minus B and y to be equal to B minus A. And then x plus y and x and y have the same color. That's it. So the bound here is terrible, right? I mean, since we use Ramsey's theorem, so it's gonna be a huge number. In fact, so let me add a, so this is the end of the proof. It's known that 1 up to n has at least 1 over 22 n squared and little I mean big O of n squared, big O of n monochromatic triples of the form x, y, and then x plus y. Okay, so when n is large, the number of triples of x, y, and x plus y having the same color is at least n squared over 22 up to certain errors. So, so as long as n is reasonably big, like how big? Yeah. So this already gives you many things, and this is shown to be tight. This this was proved by Robertson and Teilberg, 98, and then 99. But anyway, that's just a remark. One of the motivation for Schur to prove this Schur's theorem is the following corollary. I should say Schur, probably. So it's 1916 corollary, and this is related to the Fermat's last theorem. For those who may have heard the Fermat's last theorem, it says the x to the n plus y to the n is equal to g to the n. Right? Has no non-trivial integer solutions, which was conjectured. I mean, this has been a big open problem in mathematics, and then in late 90s, Andrew Wiles proved that it is true. Now, one of the attempts to prove this was to show it with a modulo p for some prime p, right? You may wish that maybe it has no solutions just because there's no solution modulo p. But Schur actually proved that that's not the case. So let me write this way. All right, so let n be a positive integer, and if p is a prime and large, okay, I should say if p is a sufficiently large prime, then x to the n plus y to the n equals g to the n modulo p has no non-zero solutions. Okay, in the video I made a mistake here. What I want to prove is actually instead of saying no non-zero solution, it has non-zero solution. So unlike the Fermat's last theorem, what we try to prove is that this equation has non-zero solution. So how do we prove that? So let's say p is a prime, and assume p is large so that any n coloring of numbers from 1 up to p minus 1 induces a monochromatic triple of the form let's say x, y, and x plus y. And this is guaranteed, the existence of this is guaranteed by the Schur's theorem, the previous theorem. Now, for each a in p minus 1, if a is equal to g to the I modulo p. Oh, I should say what g is. So let g be the primitive root. Modulo p. So what that means, so for those who took the number theory course, you may remember that there is g, so that 1 to up to p minus 1 is equal to g 1g square up to g to the p minus 2 modulo p. So there is some non-zero g, so that any other number is actually g, the power of g, and the existence of that is guaranteed. So I hope you can find it out. If you didn't know that, then you can look it up. So that's what's called the primitive root. So now, if a is g to the I modulo p, then we color a by I. Okay? And I is between 0 and p minus 2. So this oh no oh yeah, I'm a bit confused. Okay, all right, anyway, let's see what happens. Now the thing is that the number of coloring is p minus 1, which is not good. Let me do this way. We color a by not I. P minus 1 is big. That's too big. We color by I modulo n. Okay, so now, so the number of colors is n. So we divide I by n and then take the remainder. All right. Now, so suppose a plus b is equal to c, and a, b, c have the same color. Right? By Schur's theorem, the existence of such triple is guaranteed. And we chose p large so that inside this number, so a, b, c are from 1 up to p minus 1, you can always find such a triple. And they have the same color. So what does that mean? Why do they have same color? Because, well, a is equal to g to the n times, let's say, x plus r modular p. B is equal to g to the n times y plus r modular p, and c is equal to g to the n times g plus r modular p, right? When r is the color of A, B, C, because r is a remainder. So we are coloring each integer, non-zero integer, by I modulo n. So then what we know is g to the n x plus r plus g to the n y plus r is equal to g to the n z plus r modulo p. I can divide both sides by g to the r, so that means g to the, by dividing I mean you multiply the inverse of g, right? R times. Then what you have is g to the nx plus g to the ny is equal to g to the nz. So g to the x to the n plus g to the y to the n is equal to g to the z to the n. All right, so this means that these are non-zero solutions, right? This to the n plus that to the n is equal to that to the n, and none of this is 0 modulo p. All right, so that's the Schur's theorem. Now, here's generalizations of Schur's theorem by Rado, who was a student of Schur. It's only a slight generalization, so let me just state it, and you can easily see. For integers k1, k2, kr, and these three, there exists a positive integer n such that every r coloring of Sn induces I should say for every R coloring there exists J in 1 up to R and x1, x2, let's say kj in n of color j such that x1 plus x2 plus the x kj minus 1 is equal to xkj. So so Schur's theorem is the case when when k1, k2, all these things are 3, then when you get is Schur's theorem. And the proof is easy. You still take n to be this Ramsey number of k1, k2, kr minus 1, right? Then whenever you have complete graphs on kj vertices, which is monochromatic, so if this is a1, a2, a3, akj, then color of a2 minus a1 is equal to color of a3 minus a2, which is equal to color of akj minus akj minus 1, which is equal to color of akj minus a1, right? So you can take this to be the xkj, and this is xkj minus 1, xkj minus 2, etc., right? I mean, there are a lot of things. I mean, this Ram's theorem makes actually that all the diagonals will also be also have the same color, right? But we don't care. This already gives the proof. Of course, if you want to find the optimal bound, this is not good, right? This will give a huge bound. But anyway, it shows that such a thing exists. All right, that's it.